All right, the next chapter, object-oriented programming. Is that really a thing in Rust? No, just joking. Let's see what it is about. So yes, chapter 17, object-oriented programming features of Rust. Object-oriented programming, OOP, is a way of modeling programs. Objects came from Simula in the 1960s. Those objects influenced Alan Kay's programming architecture, in which objects pass messages to each other. He coined the term object-oriented programming in 1967 to describe this architecture. Many competing definitions describe what OOP is. Some definitions would classify Rust as object-oriented, but other definitions would not. In this chapter, we'll explore certain characteristics that are commonly considered object-oriented and how those characteristics translate to idiomatic Rust. We'll then show you how to implement an object-oriented design pattern in Rust and discuss the trade-offs of doing so versus implementing a solution using some of Rust's strengths instead. We're digging in. Object-oriented programming in Rust. Is it a thing? Do we fulfill the definitions? We'll find out shortly. Next section. Oh, I wasn't expecting that to expand out. Cool. Characteristics of object-oriented languages. There is no consensus in the programming community about what features a language must have to be considered object-oriented. Rust is influenced by many programming paradigms, including OOP. For example, we explored the features that come from functional programming in Chapter 13. Arguably, OOP languages share certain common characteristics, namely objects, encapsulation, and inheritance. Let's look at what each of those characteristics mean and whether Rust supports it. Alright, so here they're just trying to get a consensus of what features a OOP language has. Some definitions say that Rust is, some definitions say that Rust isn't. We know that Rust is influenced by many programming paradigms. We already explored functional programming in Chapter 13. This chapter is about object-oriented programming. And here they say some of the common characteristics are objects, encapsulation, and inheritance. So we're probably going to talk about Rust with reference to those three topics. Let's get it. Objects contain data and behavior. The book, Design Patterns, Elements of Reusable Object-Oriented Software by Crazcalm, Richard Helm, Ralph Johnson, and John, I'm not going to butcher his last name, colloquially referred to as the Gang of Four book, is a catalog of object-oriented design patterns. It defines OOP this way. Object-oriented programs are made up of objects. An object packages both data and the procedures that operate on that data. The procedures are typically called methods or operations. Using this definition, Rust is object-oriented. Structs and enums have data, and implementation blocks provide methods on structs and enums. Even though structs and enums with methods aren't called objects, they provide the same functionality, according to the Gang of Four definition of objects. So right here, they're sort of setting the stage. They pulled out a classic book, The Gang of Four. Really good book. You should read it if you haven't. And in that book, they define object-oriented programming in this way by saying that objects are made up of both data and procedures that operate on that data. So like methods. Methods or operations, which they mention here. And in Rust, we have that functionality. We have structs and enums, and via implementation blocks, we can add methods to those structs and enums. So they have a one-to-one mapping to the definition. Thus, according to this definition, Rust is, or at least Rust has, objects. Encapsulation that hides implementation details, which we know we have. Another aspect commonly associated with OOP is the idea of encapsulation, which means that the implementation details of an object aren't accessible to code using that object. Therefore, the only way to interact with an object is through its public API. Code using the object shouldn't be able to reach into the object's internals and change data or behavior directly. This enables the programmer to change and refactor an object's internals without needing to change the code that uses that object. They just defined encapsulation right here, and they're going to go over and do this in an example. So let me read this before I summarize. Cool. We discussed how to control encapsulation in Chapter 7. We can use the pub keyword to decide which modules, type, functions, and methods in our code should be public. And by default, everything else is private. For example, we can define a struct, average collection, that has a field containing a vector of I32 values. The struct can also have a field that contains the average of the values in the vector, meaning the average doesn't have to be computed on demand whenever anyone needs it. In other words, average collection will cast the collected average for us. Listing 17-1 has the definition of the average collection struct. Alright, so going back to here. So encapsulation, which we're already pretty familiar with, is the idea of having things public and having things private. And then if things are public and private, once you have those two paradigms, everybody that interacts with your code can only interact with your code via the public API. And in Rust, they went over this in Chapter 7. If you want to review that, it's there. We use the pub keyword to make things public. And it looks like we're about to write an example. So let me open up my editor. I already have the libs.rs. So let's look at this public struct. We have average collection, and it has two fields. It has list and it has average. List is a vector of I32 and average is a float 64. And they're both private because they do not have the pub keyword. So anything that's interacting with average collection cannot directly affect those two fields. So let's just copy this and put it here. Moving onward. The struct is marked pub so that other code can use it, but the fields within the struct remain private. This is important in this case because we want to ensure that whenever a value is added or removed from the list, the average is also updated. We do this by implementing add, remove, and average methods on the struct, as shown in listing 17-2. And here's the code. Let's read through this real quick. So we have an implementation block. We have the public method add. We have the public method remove, public method average, and something they did not mention up here. The function that is not public, private, update average. All right, so let's look at add real quick. Mutable self, because it's, an implementation block. But it does take a value, which is I32. It pushes that value to the list, and then it calls self.update average. Let's go back here. This is the private one. This takes no parameters. Has mutable self, but meh. It has let total equal I32. So the total is equal to the list.iter.sum, which is the summation of the list. And the list has all the I32 values in it. And then it's setting the self.average value to equal total as it's being casted to float 64 divided by the length of the list, which is also being casted to float 64, which is mandatory because you can only divide by things of the same type, and we know that average is supposed to be a float 64. All right, so let's go to remove real quick. Remove does not take a parameter, but it does return an option I32. First line, let result equal self.list.pop. So we're popping something off of the end of the list, and then we're doing a match on it. If a value does exist, then we're calling self.update average. I see. So if a value gets removed from the list, then we need to update the average again. So that's what we're calling it. and then we're returning the value within a sum. And if the value does not exist, then we would just return none, which gives us the option. Okay, and then average, which is also public, takes no parameters, returned a float 64 because it just returns self.average. So this seemingly gives all the external code the ability to read the internal field average, at least like direct access to reading it. Cool, that makes sense. Let's copy this over, paste, good. This chapter looks like it's almost over, and we actually do not write any more code, so I'm going to expand this. Alrighty. The public methods add, remove, and average are the only ways to access or modify data in an instance of average collection. When an item is added to the list using the add method or removed using the remove method, the implementations of each call the private update average method that handles updating the average field as well, which we covered. Yeah, that's right here. So in add, they call the private average field, and in remove, they call it right here, and this is the thing that they call it. We leave the list and average fields private so that there is no way for external code to add or remove items to the list field directly. Otherwise, the average field might become out of sync when the list changes. The average method returns the value in the average field, allowing external code to read the average but not modify it. I see. So that's what they're saying here, right? Is we have this public method called average, which allows external code to just read the average, but they can't directly, touch it or modify it. Because we've encapsulated the implementation details of the struct average collection, we can easily change aspects such as the data structure in the future. For instance, we could use a hash set i32 value instead of a vector i32 for the list field. As long as the signatures of the add, remove, and average public methods stay the same, code using average collection wouldn't need to change. If we made list public instead, this wouldn't necessarily be the case. Hasset and vect have different methods for adding and removing items, so the external code would likely have to change if it were modifying list directly. If encapsulation is a required aspect for a language to be considered object-oriented, then Rust meets that requirement. The option to use pub or not for different parts of code enables encapsulation of implementation details. Alright, so here they're going over, well, let's start here. Here they're going over sort of the benefit of encapsulation, which the Gang of Four book hounds and goes over it repeatedly. Which is that you have, let's take a step back. You have your public API and you have your internals, right? Everybody's interacting with your public API. So as long as your public API stays the same, then the entire world that is accessing this code does not have to change. However, what this also means is that as long as the public API is the same, you can change the internals however you want. So in this example, they mentioned changing the list from vector to hasset, which may have been done for optimization reasons. I do not know. As long as once you make this change, everything, the public API, remains the same and works as expected, at least the way the world expects it to work, nothing else has to change. Encapsulation, that's it in a nutshell. And then what they mentioned down here is if encapsulation is a required aspect to be considered object-oriented, then Rust checks off that checkbox because we have it. All right. Inheritance. Inheritance as a type system and as code sharing. Inheritance is a mechanism whereby an object can inherit from another object's definition, thus gaining the parent object's data and behavior without you having to define them again. If a language must have inheritance to be object-oriented language, then Rust is not one. There is no way to define a struct that inherits the parent struct's fields and method implementations. However, if you're used to having inheritance in your programming toolbox, you can use other solutions in Rust, depending on your reason for reaching for inheritance in the first place. Alright, so here they go off by defining what inheritance is. And inheritance in a nutshell is you have a parent class, you have a child class. The parent has fields and it has methods on it, right? When a child inherits from this parent, then without doing anything, this child by definition, by default, gains all of the properties of the parent. So it gains all of the fields and it gains all of the methods. And then if the child wants, it can override those methods. I believe that's polymorphism. But it has those options. But inheritance by default is just that association between the two. And they're stating here that if that is a concrete requirement to be an object-oriented language, then Rust isn't one, because we can't do that. There is no way that we can write a struct, a parent struct, and a child struct, and have this child struct inherit all of the properties and fields and implementation details of the parent. We just don't have that. Sorry. But we have other things that can supplement that, depending for your reasons for using inheritance in the first place. You choose inheritance for two main reasons. One is to reuse code. You can implement particular behavior for one type, and inheritance enables you to reuse that implementation for a different type. You can share code in Rust using default trait method implementations instead, which you saw in listing 10-14. When we add a default implementation to the summary method on the summary trait, any type implementing the summary trait would have the summarized method available on it without any further code. This is similar to a parent class having an implementation of a method and an inheriting child class also having the implementation of the method. We can also override the default implementation of the summarized method when we implement the summary trait, which is similar to a child class overriding the implementation of a method inherited from a parent class. So here, we're just going over how we can use traits in a similar way to inheritance in terms of the things, at least for methods, that are given from the parent to the child. So in a trait, like we did in chapter 10 with the summary trait, you can define a default method on a trait, right? And then every struct or everything that's implementing that trait by default will have access to that default method. And if you want, you can just use that default method, or you can override it. This is similar to a child inheriting from a parent and then having the option to either use the parent's method or override it. So we have that part of the functionality. The other reason to use inheritance relates to the type system, to enable a child type to be used in the same places as the parent type. This is also called polymorphism, which means that you can substitute multiple objects for each other at runtime if they share certain characteristics. And now we have a blue blob. Polymorphism. To many people, polymorphism is synonymous with inheritance, but it's actually a more general concept that refers to code that can work with data of multiple types. For inheritance, those types are generally subclasses. Rust instead uses generics to abstract over different possible types and trait bounds to impose constraints on what those types must be. This is sometimes called bounded parametric polymorphism. Alright, so right here, they're describing what polymorphism is, right? And to be clear, they're saying that enables a child type to be used in the same places that a parent type can be used. So let's say, we start from the definition, we have a parent type and we have a child type. And we have a method that takes a parent type, right, as the parameter. By polymorphism definition, we can now also pass in the child type, which is another object that is not the parent, and still use it to satisfy this function or definition. And it'll be used in the same way, all of the same things would be called, right? That is how typically we think of polymorphism. And the fact that they used parent and child in that definition is how we like mentally tightly couple it with inheritance, but that's not necessarily the case. So what they're saying in this blue blob is that polymorphism is not only different from inheritance, but it's actually a broader and more general concept. And that concept refers to code that can work with data of multiple types. For inheritance, that's typically subclasses, but in terms of Rust, what we're doing is we use generics and then we also use traits. So for an example, we can have a function that says it has to satisfy traits A, B, and C. And then as long as struct 1 and struct 2 satisfy those constraints, those traits, then they can both be used into that function synonymously. And that is polymorphism in a nutshell. And the way they describe it, or what that term means directly, seemingly, is bounded parametric polymorphism. Inheritance has recently fallen out of favor as a program and design solution in many programming languages because it's often at risk of sharing more code than necessary. Subclasses shouldn't always share all characteristics of their parent class, but will do so with inheritance. This can also make program designs less flexible. It also introduces the possibility of calling methods on subclasses that don't make sense, or that cause errors because the methods don't apply to the subclass. In addition, some languages will only allow a subclass to inherit from one class, further restricting the flexibility of a program's design. Alright, so just to summarize this. This is very true. In recent years, inheritance has fallen out of favor. And one of the reasons, the main reason they're stating here is that it's often at risk of sharing more code than necessary. So let's give an example, right? Let's say you have a parent class and then you have a child class. Now, it is not always the case that the child class needs every method on the parent class. But regardless of whether or not it needs every method on the parent class or every field, it's going to inherit it, which can at times lead to mistakes like the child class, a method that shouldn't be called because it exists on the parent is being called on the child class, and that leads to errors or similar things like that, right? And the core of this is that the parent is just oversharing with the child. All right, so here they state, in addition, some languages will only allow a subclass to inherit from one class, further restricting the flexibility of the program's design. So what they're hinting at here is that inheritance does not stop at one class. You can typically do multiple inheritance, as in you can have one class here that inherits from A, B, and C, and then all of that code is, the child has access to all of the code of all three, which is defined by multiple inheritance. But because this idea of oversharing is a thing, some languages just restrict it, say you can't do it. You can only inherit from one. For these reasons, Rust takes a different approach, using trait objects instead of inheritance. Let's look at how trait objects enable polymorphism in Rust. Alright, so that's the end of the video. If you like the video, hit like, subscribe. Outside of that, I'll see you next time. Peace. Oh, wow, that was weak. I'm a little sick. Peace.